Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial System Engineering. This lecture is on multivariate time series analysis. In this lesson, I will illustrate extension generalization of the VAR model. Specifically, I'll discuss extensions of the VAR model for non-stationary time series, including two components, a deterministic component specifying seasonality and trend, and a component reflecting exogenous variables. The basic VAR model may be too restrictive to represent the main characteristics of the data. In particular, other deterministic terms such as a linear time trend or seasonality may be required to be incorporated in a model to represent the data properly. Additionally, stochastic exogenous variables may be required as well. The general form of the VAR model with deterministic terms and exogenous variables is given by the model formulation as on the slide. In this formulation, dt is a matrix of deterministic components and xt is a matrix of exogenous variables. I'll introduce those two components in the next two slides. The deterministic component can specify both trend and seasonality whenever those are present in a time series. Using the R statistical software, we can specify trend in three ways: none, only as a constant, or as a linear trend with respect to time. This it allows for three options: a trend, both, or none. If we'd like to represent more complex trends, then we will need to write our own function to modify the VAR command. For modeling seasonality, the VAR command in R allows modeling that through a deterministic component specified as seasonality. Specifically, we need to, the VAR function in R only specify dummy variables for seasonality using the seasonal option, but it does not allow for seasonality model using the harmonics variables, for example. Thus, if seasonality has a long seasonal periodicity, we'll add many more parameters to be estimated. What are exogenous variables? Assume we have a time series yt, or a multivariate time series yt, model as on a slide. xt is exogenous if its lagged values and possibly its contemporaneous value aid in predicting yt. However, yt does not aid in predicting xt. As on the slide, the model for xt can depend only on the lag values of xt, but not on the lags of yt. This also means that xt grandeur causes yt, but yt fails to grandeur cause xt. Thus, VAR-X model allows to fit smaller models for xt while accounting for temporal relationship of xt onto yt. Another extension of the VAR model is the so-called structure VAR model, which is an extension of the VAR model by considering a linear transformation of yt through the a times yt on the left, and or a linear transformation of the error term through the term b times epsilon t. The structure of VAR models not only models lag temporal relationships, but also contemporaneous dependencies between the time series through the transformation matrices A and B. We can further write the model in the reduced form by multiplying both sides, the left and the right sides, with the inverse of the matrix A, assuming it is invertible. The reduced form has only a transformation of the error terms, thus accounting for the contemporaneous relationships through the error term alone. It is a VAR model with correlation in the error term specified by the matrix gamma. This is an example of a bivariate VAR1 of water equal to 1 model. As provided in this example, the YT1 depends on a contemporaneous YT2, since in the equation for Y1T, the term A12, the coefficient A12 is non-zero. The same for Y1T, which depends on a contemporaneous Y1 through the coefficient A21. The error terms are assumed to be independent but with different variances. We can rewrite this model in the matrix form as on the slide, where the vector time series Y1T, Y2T is multiplied by a 2 by 2 matrix with rows, with the first row 1 and A12, and the second row A21 and 1. We can further write the model in the reduced form as provided on the slide. It's important to remember that structure VAR needs to impose some constraints on the matrices A and B. This is because of so-called identification issue. That is, the parameters in the structure VAR are not identifiable because they cannot be estimated uniquely. That is, given values of the reduced form pi 1, 1, pi 2 to pi p, and the covariance matrix of the error terms sigma, we cannot estimate uniquely the parameters of the structure VAR model given by A, B, pi 1 star, pi 2 star, to pi p star. If we take the example provided on the previous slide, the reduced form has 9 parameters, where the structure VAR has 10 parameters. That is, we'll try to estimate 10 parameters using a system of 9 equations. From basic linear algebra, we know that such system cannot provide a unique solution. In order to estimate the corresponding structure VAR model, we'll need to add one constraint on the parameters such that we have 10 equations or 8 parameters to estimate. Different restrictions can be on A, on B, by imposing B to be an identity matrix. In this case, we have an A model. We can have restrictions on the A matrix by assuming that is an identity matrix having a B model, or we need to impose restrictions on both A and B when we allow for both an A-B model. Estimation of the structure VAR model means estimation of the reduced form model, then mapping back to the structure VAR model. In order to estimate the reduced form, we generally consider a two-step procedure. First, apply the estimation approach just as the simpler VAR model to obtain the estimates of the coefficient matrices pi 1 to pi p. Then take the residuals of the model fit and estimate their covariance using the sample covariance. Here is a simple example. If we assume a bivariate time series when we fit it with a VAR model of order 1, with the restriction that A12 is equal to 0, we estimate the reduced model to get the estimated coefficient matrices and the estimated covariance matrix. We can estimate the only unknown coefficient on the A matrix from the estimated covariance as provided on the slide. As in this case, if we impose a sufficient number of constraints, we have a one-to-one correspondence between the reduced model and the structure VAR model. In summary, in this lesson, I introduced 2 extensions of the VAR model, specifically the VAR-X model and the structure VAR model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is a multivariate time series analysis. On this lesson, I will introduce another concept that applies to an extension of the VAR model, specifically cointegration. Thus, from the previous lesson, from generalizing using the VAR-X model, which allows for seasonality and trend, and structure VAR model, which allows for contemporaneous relationships, now the generalization allows for non-stationary VAR model, which can be dealt using differencing approach. In a different lecture, we learned about an approach for dealing with non-stationary time series, specifically differencing the time series. This concept applies generally to both univariate and multivariate time series and is formally defined as integration. To be more specific, if the d-order difference of a time series yt is stationary, we define that yt is integrated of order d, or more concisely, write yt tilde I of d. I of d is an indication, is a definition of integrated time series of order d. If d is equal to 0, then a time series yt is stationary. Thus, we do not need to take any difference to make it stationary. When d is equal to 1, then only a order equal to 1 difference is sufficient to obtain a stationary time series. While integration means taking a d-order difference of the time series, co-integration means taking a linear transformation beta of the vector time series yt, where yt is a multivariate time series such that the resulting linear combination is a stationary time series. The linear combination beta transpose yt is often motivated by economic theory and referred to as a long-run equilibrium relationship. It's important to know that the vector beta is not unique in making the linear combination of the multivariate time series stationary. We can multiply this vector with any value, with any constant, which will result in a rescaled time series. This will not change the stationarity property of the linear combination beta transpose yt. Thus, we need to impose a constraint on the element of the vector beta in order to have a unique linear combination. This is called normalization. A typical normalization is to consider a vector of the coefficients in which the first value in a vector is 1, as the vector beta provided on the slide. Using this vector beta, if we multiply y beta transpose with yt, we'll get y1t minus beta 2 y2t up to beta n ynt equal to ut, or the equation provided on a slide where y1t is equal to this linear combination of beta and contemporaneous values of the time series plus ut. Ut is a cointegrated residual. Ut is a stationary time series. For an n-dimensional multivariate time series, we can identify up to n-1 such cointegration relationships. For example, if we consider a trivariate time series with n equal to 3, there may be two different cointegrating vectors, beta 1 and beta 2, such that the linear combinations using these vectors result in stationary time series. These two vectors are linearly independent, otherwise they will lead to the same cointegrated relationship. The matrix B, with each row corresponding to one cointegrating vector, is called the cointegrating basis. Two important properties are as follows. One is that both vectors need to be normalized to be unique, as discussed on the previous slide. Second property is that any linear combination of the two vectors leads to a cointegrating vector. This is why B is called cointegrating basis, since the two vectors are the basis of any other cointegrating vector. Let's now consider a multivariate time series with n time series, which is of integration of order 1, meaning that linear combinations are sufficient, that one order or linear combinations are sufficient in transforming the multivariate time series into a stationary time series. Similarly, as for n equal to 3, we can identify up to n-1 different unique cointegrating vectors, which will form the cointegrating basis as in the previous slide. Cointegration hypothesis tests cover two situations. One is that there is at most one co-integrating vector. The other is that there are multiple co-integrating relationships. These two approaches have been introduced in the references provided on the slide. Let's take a closer look at these approaches. First, let's define the hypothesis. In testing for co-integration, the null hypothesis is that of co-integrated multivariate time series, assuming an integrated time series of order 1, and the alternative is that the multivariate time series is stationary. Note that this is not a test of stationarity, it is a test of co-integration. The general approach proposed by Engel and Granger is that of two-step method. First, form the co-integration vectors and test whether the residual time series is stationary, thus employing a test for stationarity. There are two situations here. One is when the co-integrating vector is known. The other is when it is not known. When the co-integrating vector is not known, it can be estimated from the data, assuming that it's co-integrated. To note, when the basis is not known, some normalization assumption must be made to uniquely identify it. We can expand the idea of co-integration to VAR models. Let's consider the classic VAR model with a deterministic component. VAR is stable if and only if there are no roots of the VAR polynomial in the unit circle. Moreover, stability implies stationarity, but not the opposite. Stationarity condition is less restrictive. A VAR is stationary if there are no roots in modulus that are exactly on the unit circle. If there are roots on the unit circle, then some or all of the time series in YT are integrated of order 1, and they may be also co-integrated. If YT is co-integrated, then the VAR representation is not the most suitable representation for analysis because the co-integrating relationships are not explicitly apparent. The co-integrating relationships become apparent if the VAR is transformed to the vector error correction model, abbreviated as VEC-M. VEC-M is particularly of interest in the interpretation of the relationships between the time series by introducing concepts such as long-term relationship between variables and the associated concept of error correction, whereas one studies how deviations from the long run are corrected. The VEC-M is described on the slide. In this definition, the matrix pi is 1 minus the sum of the pi I matrices in the original VAR model. This first component, pi times yt minus 1, is the only part that can be integrated of order 1. All other components are differences of the lags t minus 1 to t minus p plus 1 and hence are stationary. To ensure that the model is identifiable, we need to assume conditions on gamma, k, and pi matrices as provided on the slide. I will not expand further on this model since it requires more advanced modeling. Its application is more relevant to understanding relationships between time series rather than forecasting. In summary, in this last lesson, I introduced an extension of the VAR model which allows to model multivariate non-stationary time series. Thank you.